Good. Oh, I guess I need facing, so I have extra space. All right. Yes, so repeating what I said a moment ago, for the sake of not introducing too much new content when we have it on practice, there's no new lecture content, so I'm not using an integer session number. This is mostly because I've committed myself to only doing, 10 sessions on applications of integrals, so we have to, truncate or stop at 60 or something. So in order to stop myself from getting close to having to truncate, I will choose 55.5 as the session number and just do a bunch of problems. Mostly you'll be doing the problems because they're all phrased as challenges. So, okay, good. They won't be especially interesting, so first let's just do a quick review of what we discussed last time, and then I'll give you some, kind of brain-dead warm-up exercises, but the main point of the discussion of probability distributions we had last time was that all a probability distribution is a real valued function on the entire real line with two properties. So it only outputs non-negative values, so the range is only from 0 to infinity, just because the probability of something happening is supposed to be a non-negative number, and the total integral is supposed to be 1. It's just because if this f is supposed to represent the probability density per unit length of something happening, then when you add up all of those densities for little chunks along the line, you had better get 1. Just because if x is a random variable that you can generate by some process, when I run that process to generate something, I have to get some answer, right? If this entire integral were a half, that would mean that half the time I run the process and I just don't get an answer, which wouldn't make sense. So anyway, good. If f of x is such a real
Secretly, it makes total sense, as in buggy code.
Well, yes, if you run and half the time you just don't get an output, then you can have a probability distribution that sums to less than 1. But let's assume that's not the case.
That's not the point.
Yeah, if we have debugged, so that does not happen. But good. So if f is a function satisfying those properties, those two things here, we say that f is the probability distribution for a random variable x if the probability of getting an instance of x in some interval from a to b is given by the integral from a to b of that density. Right, so this is very much like the definition of density for a mass distribution, right? If you want to get the total mass of, a rod with varying density between 2 points a and b, you just integrate the density over that range. And this is just saying now, to get the total probability of lying in an interval, you integrate the probability density over that range. Good, so we saw that last time. And then we also defined the expectation value. This is also sometimes called the first moment. And then in the next integer valued meeting, when I introduce new content, we'll see the second moment and higher moments and how those relate to the moment of inertia. But anyway, the first moment is just somehow the average value you would get from...
So,
yeah.
While I'm remembering to ask, is there a second moment of inertia in regular, quote-unquote, regular physics? Even though physics is calculus and all that jazz.
No. So in physics, what we mean by moment of inertia is second moment. So in physics, moment of inertia should really be called the second moment. Oh, I can't spell inertia. Inertia. The moment of inertia is the second moment. And sometimes, especially engineers, you'll hear them actually call this the second moment of inertia. So the thing which has to do with rotating, right? Remember we derived this by saying you have some object which is rotating and you want to know its total kinetic energy, and we wrote that as Ke is 1/2 I omega squared. So that thing, the thing that appears in the kinetic energy of a rotating object, is the second moment. So there's no higher moments of inertia, but there are different moments of an object. So the first moment in physics for a massive object is just the center of mass, right? And the 0th moment, which is just the integral of the density, the 0th moment is the total mass of the object. So it makes sense to talk about higher moments of objects, but you don't say the word inertia. The word moment of inertia specifically means the second moment, and the other moments have different names, right? The 0th moment is the mass, the first moment is the center of mass, the second moment is the moment of inertia, the third moment is less useful, but you could think of it as something called the kurtosis, or skewness.
Yeah, I was about to say. You say it's less useful. What is it?
Yeah, I mean, it's super useful in finance. If you don't model the third and fourth moments of a price distribution, you're going to lose a lot of fucking money. But in physics, the third moment is it's less useful. It's some
Is there a way to describe it?
yeah. It's just saying is the distribution of the mass in your rod lopsided? So if you have some rod, the first moment tells you where's the center, the second moment tells you roughly how is the mass distributed about the center, so is it far away from the center or is it close to the center? That's the second moment. The third moment tells you, okay, I know how far away it is from the center, but is the farness away from the center more on the right or more on the left? Right? If the farness away from the center is more on the right, then the third moment is positive, and if it's more on the left, then it's negative. So it's the asymmetry of how far your stuff away is from the center of mass. The asymmetry. Is it more on the right or the left? That's
And
the
I assume applying higher moments to physical things gets less and less useful.
Yeah, it's less useful for rods just because there's no fundamental physical quantities like kinetic energy that depend on the higher moments, the third and fourth and so forth. It's incredibly useful in probability because in probability you care about what data do you need to reconstruct a probability distribution. And as it turns out, for reasonable probability distributions, if some guy on the street just walks up to you and hands you an infinite list of all the moments, so he's like, here you go. Here's the 0th moment, the first, the second, the third, the fourth. He gives you all of them. So here's a list. Can you tell me what the probability distribution is? Right? Can you just tell me like exactly what is the function? And the answer is, for a certain class of probability distributions, the answer is yes. If you know all the moments, you know the entire graph. Like, you can just write it down. As we'll see later today, that doesn't work for all of them. There's actually very reasonable looking distributions, even ones that come up in science, where the moments don't exist, where they're not even defined. So for those guys...
So, random, I guess, marginally related thought. Is this on par with being able to be given an output at a certain derivative of a polynomial and being able to find the polynomial?
Yeah, okay. It's exactly the same, actually. So you could ask, if I have a function f of x, and I tell you all of its derivatives at, say, some point. So I tell you, well, okay, so I'll put a question mark here. We want to know what is the whole function. If I tell you the value at f of 0, so okay, fine, I tell you how high the output is at some value, say 0. I tell you the slope at 0, so I tell you how much it's changing. I tell you the second derivative, which, as we've seen, is something to do with like how different are nearby points away from the average. And then I tell you the third derivative and so forth. And I tell you every derivative of this function at a point 0. You could ask, all right, if you know all of the infinitely many derivatives, can you just write down the function everywhere?
Oh, yeah.
Yeah, and we discussed this. And the answer is yes, if it's analytic. So yes, if analytic. So for an analytic function, if you know all of the derivatives, or equivalently, if you know all of the values in a small range around a given point, you know the entire function. But analytic is a very special property, right? Not all functions are analytic. So for non-analytic functions, I could give you all of the derivatives, and you don't know what the fuck it's doing far away from that point, just because it can do kinky shit, because it's not analytic. In the same sense, probability distributions can do kinky shit, where knowing all of the moments doesn't tell you what it's doing everywhere. But under certain assumptions of niceness, if the probability distribution is sufficiently nice, knowing all of the moments tells you what it's doing everywhere, in the same sense that knowing all the derivatives, even just at one point, tells you what the function is doing everywhere if it is sufficiently nice. Yeah.
I assume analytic has a much better definition than this.
Yes, and this will be the topic of Chapter 7, which is infinite.
Oh boy!
So this has been hinted at in 1802 when someone said something about having memories of Taylor series expansions, maybe traumatic memories. So the definition of analytic, so analytic equals, the literal, what this means is it has a convergent, so I'll write convergent Taylor series. That's all it means. So if you're analytic, you have a convergent Taylor series expansion. That's all it means. So As you may have suspected, we will discuss Taylor series in the chapter on infinite sequences and series, which follows this chapter. So that will be sessions 60 through 70. Good. Other thoughts?
No thoughts.
Okay. Alright, so that's everything from last time. Probability distribution, first moment, and don't forget these things. It has to be non-negative, it has to integrate to 1, basically. Okay, so a very simple example, which I just took from an AP Calculus course, which you can probably tell by how brain-dead this function looks. So if someone hands you this function, it's f of x is x cubed over 5,000, some stupid number, which is chosen for a particular reason, you'll see, x cubed over 5,000 times the quantity 10 minus x. And that's only true, so it's kind of piecewise defined. You can actually think of this as being, f of x is that junk, x cubed over 5,000 times 10 minus x, only for 0 is less than or equal to x is less than or equal to 10, and 0 else. So you have this function which is only non-zero between 0 and 10, it's 0 everywhere else. And then the first part of this question asks us to prove that this function is in fact a probability density, or a probability distribution. So what two things do I need to show to convince the reader that this is actually a PDF?
So we need to show that integrating over it from 0 to 10, since negative infinity to infinity is pointless.
Yeah.
At x times f of x dx equals 1.
Not x times f of x, just f of x. F is the probability. So
Whoops.
this is the average value, but the average value doesn't have to be 1. It's just the total probability has to be 1. This is a probability density. So
clarified.
Good. Okay, yeah, so, well, I mean, we also have to prove it's positive, right? We have to, or non-negative, but that's pretty easy because, I mean, by construction, if x is positive, x cubed is positive, and if x is between 0 and 10, then 10 minus x is certainly non-negative, so the first part is pretty easy, right? So this thing is obviously non-negative on this interval, so indeed all we have to do is integrate this guy from 0 to 10. So what is that integral?
So it's x to the 4th over 5,000 times 10 to the negative x. No, it is x to the 3rd over 5,000. I was over. Yes, I know what I'm saying. It is x to the 3rd over 5,000. Give me a second to get my thoughts together, because I'm getting overconfident. The integral from 0 to 10 of x to the 3rd over 5,000 times 10 minus x dx.
Yeah. So this is what?
Well, let's see. Equals 10x to the 3rd over 5,000 minus x to the 4th over 5,000.
So you just distributed...
Still an integral. Yes, I'm distributing.
Okay, so as you say, 10x cubed over 5,000 minus x to the 4th over 5,000. You can even pull out the 5,000 if you want, but sure. This is true.
Whoops.
Alright, so then what's this?
Hey, we should probably pull out the 5,000.
Okay, so I'll pull out the 5,000, and then what goes in the big brackets when I do the power rule on these guys?
Let's see. So 10x to the 4th over 4.
Good. And the second term?
Minus x to the 5th over 5.
X.
From 0 to 10.
Okay. So at 0, this gives us nothing. What happens at the top endpoint?
It says unevaluated big... Well, no. We gotta show that this is 1. That's for B. That's for B, yes. Oh boy. 10x to the 4th over 4 minus 10 to the 5th over 5. I mean, 10 times 10 to the 4th.
10 to the 4th is 10,000, in other words, so good. Minus 10 to the 5th, well, 5 zeros means 100,000, right? So
yes.
Over 5, and then this is how you know it's an AP Calculus question, because it actually wants us to do some fucking arithmetic, but okay, so what happens in parentheses now?
100,000 over 4 minus 100,000 over 5, oh god.
100, yeah, so 100,000 over 4 is what, 25,000 in most countries. And
Yeah.
100,000
Minus 20,000.
Aha! Now you see why this 5,000 appears. So,
Equals literally 1.
good. 5,000 over 5,000 is, in most countries, equal to 1. Good. Yes, so now you see that this overall number, 5,000, was cooked up precisely, precisely so that this thing would be a probability distribution. So that's good. All right. Questions on A?
Nope.
Okay. Good. So then, now, I mean, I'm not going to... As you can probably tell, the way that the question was originally written did not have these unevaluated big boys comments, but I put those in just because I don't want to do any more math, and by math I mean arithmetic. So, all right, let's ignore the evaluation of these things and just write down the integrals and, do the power rule, but not plug in numbers. So if I wanted to find the probability, when I run this process, I generate some x, described by this PDF. What is the probability that the output lies in the interval from 1 to 4 as an integral?
1/5000th times the integral from 1 to 4 of 10x to the third minus x to the fourth.
Yeah, so 10x cubed minus x to the fourth. And now you can probably tell this is actually going to just be the same integral but evaluated at different endpoints. So if you remember what we wrote down a moment ago, what goes in the big boys for this guy?
Is going to be 10x to the fourth over 4 minus x to the fifth over 5.
Yeah. Good. So same thing, but I'm
4
not...
4 times 52.
Yeah.
20. Well, yeah. It says unevaluated big boys, but I want to show off my Minecraft 16 times 16 skills.
Well, yeah, I mean, if you've memorized powers of 2, like I also have, I mean, I happen to know 2 to the 8th is 256 and 2 to the 9th is 512, but it doesn't matter because, I mean...
Because we don't care.
Yeah, I mean, when you plug these in, I just put it in a calculator, I got something like 0.08 or in percent 8%. So, I mean, I don't give a fuck, but the point is that if this were your PDF, then the probability you would get something between 1 and 4 is about 8%. Okay, and just for the sake of doing all of the parts, this is going to be, again, the same integral, but with different endpoints. So what should I change about the endpoints in this calculation if I now want to find the probability?
6 to 10.
Yeah, 6 to 10. In particular, not infinity, because it only runs up to 10. Good, so 6 to 10.
Well, going up to infinity wouldn't be wrong. It also wouldn't be quite right.
Well, it actually would be wrong in this expression, because plugging in infinity for this expression is going to give you a problem.
Right, because this is assuming that it's less than 10 when we do that integral.
Yeah, because we have explicitly plugged in the value of the function, which is only valid up to 10. So if we wanted to run this up to infinity, we would have to use a piecewise function that is 0 past 10.
Yeah.
Good.
Piecewise integrals, that's...
Well, it's not hard, you just split it into pieces, but...
Oh, yeah.
But, good, okay, indeed. So, yeah, just replacing literally the same expression with now 6 to 10, if you put this in a calculator, you'll now get about 66%. So, oops. Actually, most of the probability for this PDF lies in the range from 6 to 10. But fine, okay, I mean, it's a kind of a boring problem, but it's...
So how do you find the point where it equals, exactly 0.5?
Oh, if you want to integrate up, well, I mean, you could solve this equation. You'd ask, for what value, integrate from, say, 0 to x, or to I don't know, y or something, and set that equal to 0.5. Then you just have to solve some fourth order equation, which is kind of a pain, but you can put it in Mathematica if you want. I don't know what the answer is by staring at this, but, we could figure it out. Good.
Wait, would that... I'm trying to remember. Would that be the same as the center of the mass? Well, center of mass, quote unquote. You can't see me air quoting over here. Would that be the same value as the center of mass of the set? I mean, probability function?
So the point at which you have to integrate up to... Yeah. So the point at which half the probability lies to the left and half lies to the right is indeed the center of mass. Quote unquote, as you say, because if the probability distribution were a mass distribution, then yes, exactly the point at which half the probability is to the left and half is to the right would correspond to the center of mass for the mass distribution. Yeah, good. Okay,
Lovely.
a new problem. Okay, so last time we met some probability distributions like the Gaussian and this Maxwell-Boltzmann distribution for ideal gases or something. So now we'll meet a new one, which is called the exponential distribution. So the exponential is a distribution which is only non-zero for positive values. So it's modeling some number which really should only be positive, and usually the interpretation of this number is how long you have to wait for something to happen. So I actually first encountered this distribution in finance when we were interviewing people at Domeyard trying to find experts for our market making strategy. So in market making, you submit some what's called a limit order. So you submit an order to the market saying, I'm willing to buy or sell at this price. And then you have to wait until you get matched, so to speak, or get filled. You wait until someone is willing to buy or sell at your price. And when we interviewed someone and asked, all right, so in your market making strategy, how do you model the wait times for getting your order filled? And he kind of like hedged for a second and looked away, and he's like, all right, I don't mind spilling the beans. I don't mind telling you guys this secret because every schmuck on the street knows that you use an exponential distribution for this, which I thought was very funny. So he proceeded to tell us how they at Goldman or wherever he worked, they used exponential distributions. So anyway, the moral of the story is if you're trying to write down a distribution function for how long you have to wait for something to happen, where this is f of x, and x is like a time in, say, I don't know, minutes or something, you have to wait for something to happen, usually the exponential is the way to go. And you have to pick this number lambda so that it fits whatever data you want. But anyway, all right, so that's just some flavor. So first, in part A, we want to verify that this thing is actually a distribution function, assuming lambda is positive. So we have to do two things. One, show that this is non-negative, but if lambda is positive, that's very easy because the prefactor lambda is positive and e to the x is always going to output a positive number, so this thing always gives us something positive. So that part's easy. What else do we have to check to verify that this is a PDF?
We have to show that the integral from 0 to, well, yes, the integral of f of x from 0 to infinity equals 1.
Yeah, good. So let's do that. So from 0 to infinity of lambda e to the minus lambda x dx, and what is that equal to? Where lambda is a constant.
Oh, lambda is a constant. Oh, that makes it much easier. In that case, it is going to be lambda e to the negative lambda x times negative lambda.
Lambda.
So,
well, okay, so what goes in the brackets when you anti-differentiate this thing? So you pulled out a lambda, that's fine. What's the anti-differentiate?
yes, it's integrals. So it's e to the negative lambda x over negative lambda.
Yeah, so times, I don't know, 1 over minus lambda or something. And this is at 0 and infinity. So infinity is easy. What happens at infinity for this guy?
At infinity, it goes to 0.
Yeah, this guy gets totally murdered at infinity. So this is really lambda times 0 minus what happens at 0.
0, it's equal to 1.
Well, this is equal to 1, but then we still have to multiply by 1 over minus lambda.
Oh.
So 1 times 1 over minus lambda. Right?
And thus it is 1, well, let me see. The right side is equal to 1 over lambda.
Yes, this is lambda times 1 over lambda, which is, of course, equal to
equals 1.
Good. Yes. So
yes.
As it should be, the total probability is equal to 1. Because if you're going to ask, how long you have to wait for something to happen, the answer to that question had better be something. Good. Okay. So now another question. So if indeed f of x is a waiting time, and I want to compute the probability, I have to wait at least 6 minutes. So maybe x, the units of x, for instance, could be minutes. So if I want to find the probability, I have to wait at least 6 minutes. So the probability I wait 6 or more minutes. What integral should I write down to get that?
I believe it is the integral of lambda e to the negative lambda x from 0 to, not 0, 6 to infinity.
Yeah, good. So we just integrated this, so what goes in the brackets again?
That is going to be e to the negative lambda x times, all over lambda, or times 1. Yes, it is a negative, thus it is negative 1 over lambda.
Not 0, sorry, 6.
6.
Good. Good. So
at infinity, this term goes to 0, and at 6, wacky stuff.
Yeah, we just put in a 6 for the x, right?
E to the negative lambda times 6 times negative 1 over lambda.
Times 1 over lambda. Yeah, so we subtract the value at the lower endpoint. So we're subtracting something times minus 1 over lambda, but those two minuses combine to give us a plus.
Right.
And then it cancels very nicely because there's a lambda outside, which cancels with the 1 over lambda downstairs. So overall, it's just e to the minus 6 lambda. Right?
Is it always going to be e to the negative lambda times time in this case?
Yeah, it's always true that if you integrate from any lower number b up to infinity, lambda e to the minus lambda x dx, the answer you will always get is e to the minus b lambda. Yeah, so it's just the lower endpoint. Right?
Whoa.
Yeah, I mean, it's not magic, it's just how the exponential works, but good. Okay. So, yeah, as you say, it's not hard. You just do this integral. In the first case, we're finding the total area everywhere and want to show it's 1. And indeed, plugging in 0 and infinity, you get 1. The second piece, we ask, now it's between 6 and infinity, and when you plug in, you get e to the minus 6 lambda. Oh, sorry, I think I said what a moment ago was it was e to the b lambda, but it should really be e to the minus b lambda because of the minus sign. Sorry. But good. Yeah, the point is you could ask, given this process, what should lambda be, right? It seems like lambda was just undetermined, and the answer is, yeah, you would pick your lambda based on the process you're trying to model. Because obviously, if you're trying to model the time it takes for you to wait for the bus to come versus the time it takes for you to get a fill on CME when you're a high-frequency trader, those times are going to be very different because you could wait 20 minutes for the bus and 20 microseconds to get filled on CME. So you pick your lambda appropriately for the problem at hand. So
okay, without context, I can't tell if CME is something financial or something prescription.
CME is the Chicago Mercantile Exchange, so it's very much financial. It's where you buy futures contracts. So what we used to trade were these contracts for like ZSH6 or something, which is like a futures contract for 50,000 barrels of wheat that will be delivered to you 6 months from now or something. So it's just stupid shit. Futures contracts that like Kellogg or someone who makes cereal might buy. But anyway, yeah, so on CME, these would be kind of, short times, so therefore large lambdas, but if lambda's in minutes and lambda were 0.1 inverse minutes, say, then the probability I'd have to wait more than 6 minutes would be like, 55% roughly.
Why do I have a vague memory of someone telling me about a time that their company bought a huge amount of some commodity and then they had to buy some place to store it because they couldn't sell it? Invested in.
Hold on. You didn't come to the high-frequency trading talk. That was before your time, right? That was 2 years ago, so you were in 8th grade. So you could not possibly have heard me talk about that then.
Wait, what are you referring to?
I'm referring to Jim Thorpe Talks 2017, right? Or no,
what event?
JT, it would have been...
What event was this?
Well, it was...
I'm talking about the, more specifically about why I remember this.
Yeah, I was going to say, it doesn't make sense, because this was in 2017. There was this schedule thing called... Yeah, I gave this talk called Fast and Smart, a tour of high-frequency trading in 2000.
Yeah, and I missed it because I was in a biotest.
Wait, did you exist for this? I thought this was...
I was there 2017. I missed that specific talk.
I see. So you could not have possibly heard that story. So who did you hear that had to take possession of a large quantity of commodities?
Tell me what your story is, and I think I will recognize it.
I didn't actually have a story. I gave in that talk an example of what could have happened if we had failed to trade out of a position in time. That like a dump truck would have shown up to the Dome Yard offices in Boston with 50,000 bushels of corn or something. But that never actually happened. So it
Okay. I feel like this was a large quantity of oil or wheat to a family's just business they were involved in.
Interesting. So it's probably not me then, unless you missed that talk and then you asked someone who did go to the talk what it was about, and they like exaggerated the story about like my talking about what would have happened if we had not traded out. They told you that that's what actually happened, and you got like this skewed impression or something.
Yeah, I have no idea, but I have no idea. That is incredible coincidence, I'd say.
Yes, unclear what happened, but okay. Well, let's do another question about this. So. Before we found the probability that I would have to wait more than 6 minutes, but another question you can ask is, what is the average waiting time? Or in more precise terminology, what is the expectation value, E of x, for the waiting time? As defined, a few slides ago.
Expectation value is going to be...
Yeah, what's this?
The integral from 0 to infinity of x lambda e to the negative lambda x.
Good, dx. So I think we have to integrate by parts to kill off this x. So what should I do?
Yeah.
Oops, what should I do for that?
We are going to be moving the... Let me see. What is the antiderivative of lambda e to... Oh, yeah. Antiderivative of e to... lambda e to the negative lambda x is going to be e to negative lambda x?
Times minus 1 over lambda, right? The same thing we saw before.
Right.
Yeah, so, well, let's do it in two pieces. So let's pull out the lambda, first of all. And then, yeah, as you say, the first thing should be, what, x times the antiderivative of e to the minus lambda x evaluated at the endpoints, right? So, and then minus the...
I'm just thinking because having the lambda in there may simplify things.
Yeah, okay, well, I mean, yeah, sure.
Whatever. Well, it'll be the same regardless.
Well, for now. So what goes in the brackets?
So in the brackets we have x times e to the negative lambda x times 1 over negative lambda.
Good. 1 over minus lambda. And then minus the integral of, I guess, v du. So what goes under the integral?
This is going to be e to the negative lambda x times 1 over negative lambda.
Yeah, the x goes away because we kind of dx, it's just dx. So, good. Okay, so we can now do this in two steps. So we can evaluate the brackets, which, as you know, well, at infinity, it certainly still goes to 0 because e to the minus lambda x dominates x, right? X is getting big at infinity, but e to the minus lambda x is getting small much faster. It totally dominates x. So this thing still goes to 0 at infinity. What happens at the lower endpoint at 0?
0 times 1 times 1 over negative lambda equals 0.
Yeah, so it gets murdered at both of them, right? So we can actually just ignore this. So this thing goes away, which is the nice thing about integration by parts when your function dies off sufficiently fast, is the boundary term just goes away.
Context. When your function dies off.
Yeah, that's how physicists say it. Your function dies off at infinity. But, okay, so now what happens in the second term?
We are going to convert this to negative times big boys from 0 to infinity of e to negative lambda x times 1 over lambda squared.
Yeah, good. So we pull out another minus 1 over lambda. The minuses cancel, and now it's 1 over lambda squared. And again, it's 0 to infinity. And I think we can evaluate this pretty easily. So then what happens?
Equals negative lambda times, let's see, infinity is equal to 0, and 0 it is equal to 1, thus
1 times...
literally lambda.
Yes, because it's 1 over lambda squared at the bottom.
Oh, right.
Yeah, don't forget the
Whoops.
second term. When you plug in x equals 0, the first term is 1. But 1 times something which is not 1, you still need the
Is
second
not
term.
1.
Yes, so it's, indeed, 1 times 1 over lambda squared, but now this works out very nicely because the minuses cancel and 1 factor of lambda upstairs cancels lambda downstairs, so the
It's
answer...
1 over lambda.
Yeah, perfect. So let's just check the units on this, by the way, because as a general rule, which will serve you well in the rest of your life, whenever you have an exponential, e raised to some number, the number appearing in that exponential has to have no units. And it's very easy to see why. If you have something with units of, say, length, like meters, what does it mean to take e to the power of meters, right? This doesn't make any fucking sense, to take a number and raise it to the power of meters. However, taking e and raising it to the power of some dimensionless number, like 1, which does not have a unit, there's no units attached, e to the power of 1 makes sense. It's like 2.718. So everything appearing in an exponential must have no units. It's dimensionless. But that means if the product of lambda and x must be dimensionless because it appears in an exponential, right? Minus lambda x appears inside e. That means that this thing, so I use brackets for units, the units of minus lambda x are nothing, which is 1. But if x is a time, right, because x is supposed to be a waiting time, right, that means the units of lambda times the units of x, which are, say, minutes, equals 1. Or, in other words, dividing by minutes, that means the units of lambda must be inverse time. So 1 over minutes, or hertz, 1 over seconds, or whatever. So the point is that if lambda has units of inverse time, 1 over minutes, then our answer makes a lot of sense because we were trying to find the average time I would have to wait for the bus. But the average time I have to wait is apparently 1 over lambda, where lambda is something with units of inverse time. So it's as though we were trying to compute a time and we got something with units 1 over hertz, right? Because 1 over hertz is 1 over seconds, which is a time. So we're in good shape, actually. The units work out. But anyway, that's a side remark, I guess. Good.
Whoa.
Other thoughts on average waiting times or units?
Nope.
Good. All right, more. Yeah, well, I mean, this is the same thing. So, right, by the definition of expectation value, x times the probability distribution. You integrate by parts, this term dies. This thing evaluated at infinity and 0 gives you roughly 1 over lambda squared, and then you multiply by lambda and get 1 over lambda. And as I say, the units are correct because of this argument I just showed you. Good. Something else. Okay, so let's meet a new probability distribution, which has a lot of names.
I thought, based off of how you were saying that, I expect you to say, let's beat a new horse.
Yes, well, you could interpret it that way as well, because we're doing the same problems over and over about expectation values, but now the horse is different, although we are still beating it in the same way, so to speak. But yeah, so...
Context.
Beating on
absolutely necessary.
Mr. Hands. Good. So this probability distribution has a lot of names, which is largely just because it came up separately in many different contexts, and different people decided to name it after themselves. So it's usually called the Cauchy distribution, after Augustin Cauchy, the French mathematician. But in particle physics, this is also called the Breit-Wigner distribution, which you use to model the lifetimes of unstable bound states in particle physics. It's also called the Lorentz distribution. So there's at least 3 names for this, but anyway, well, I don't care what the name is. What is it?
Looks like a weird bell curve.
Yeah, it's basically a bell curve with one very important difference. So the bell curve is roughly e to the minus x squared, right? So e to the minus...
Roughly or exactly?
Well, it's this with e to the minus x squared over 2 sigma squared, where it's x minus mu squared, 1 over root 2 pi sigma squared, because it has some square sigma, right? But if mu is 0 and sigma is 1, then it's just e to the minus x squared. So let's do a simple case. the point is that e to the minus x squared, as you know, dies really fast at infinity, right? Exponentials die much, much faster than polynomials. That's what we say by, this thing dominates any polynomials. So what the Cauchy distribution does is that it roughly looks like a bell curve, but it dies off much more slowly at infinity for the following reason. Because the distribution is roughly some number times a number upstairs times, something which looks like 1 over x squared plus a number squared downstairs. So this is dying off at infinity very slowly because it only goes like 1 over x squared, which goes to 0 when x is large, but it does so much more slowly than the bell curve. So this is like this is a bell curve where like the tail of the distribution, as it's called, the part of the distribution when x is very large, gets close to 0 much more slowly. But anyway, so that's, we'll see more about that in a second, but let's consider the special case where the center, x0, equals 0, and something which is called the shape parameter, gamma. The shape parameter is 1, and if I plug those in, then we just get the function f of x is roughly 1 over pi times 1 over x squared plus 1. Okay. So if this is our distribution, I'll ask you, how do I find the expectation value? What integral do I write down which would define the expectation value or the mean value of this distribution?
What is going on? Give me a second. Someone's probably yelling at me.
Ruh-roh.
Anyways. The expectation value of this is, let's see, negative infinity to infinity of x times 1 pi times 1 over x squared plus 1.
Times 1 over x squared plus 1. Okay, good. Now this is a pretty obvious u sub, so how do I do this integral now?
Okay. We let u equal x squared plus 1, and thus dx equals 2x.
Good, so for du...
Of course, I'm forgetting.
2x
yeah,
dx.
du equals 2x dx.
But, alright, so, sure. And then what?
We are going to this becomes, let's see. It looks like by the u sub, we're going to have our integral go from infinity to infinity.
Let's see. So when x is minus infinity. Oh, good. So you say, why is this? I'm confused. So
I assume it's because infinity is weird.
Yeah, we should probably, let's break this into pieces because this should really be, let's think about this before I confuse myself. So this should be integral from 0 to infinity of x over pi times 1 over x squared plus 1 dx. And then let's do the two integrals separately because we don't want to get this weird thing where the two endpoints kind of collapse to one point. So if we split it into two pieces, and then as you say, do the u sub for the first piece in the top, we can keep them separate and then recombine them at the end. So if in the first piece I do u is x squared plus 1 and du is 2x dx, and I just rewrite this integral, then what does that become?
Let's see. The top integral is going to become the integral from 0 to infinity of, well
1 to infinity, but because when x equals 0, u is 0 squared plus 1, which is 1. But good.
It is going to be the integral from 1 to infinity of 1, wait, no, pardon me. One over 2 pi times 1 over times 1 over u, right? I think. I don't know.
Sorry, I think you cut out.
dx.
Did you say 1 over u? du?
Yes.
Okay. Good. Yeah, okay, so then I think we know what this is, so what does that turn into?
It becomes 1 over 2 pi, begin brackets, log u from infinity to 1.
Good. Let's not plug that in yet, because we're going to have a problem when we plug in log of infinity. So let's just pause for one moment and see if the bottom integral saves us, because so far it doesn't seem like this is helping. But okay, so let's make the same u sub in the bottom integral, going from 0 to minus infinity. And when we do that, what does the bottom integral become?
Well, let's let's pull out a minus sign and swap the order of the thing.
Yeah, so minus, and then what, 1 to infinity now or something? So
Yes.
Good. Okay, and what happens?
This is going to become this is the same one, 1 over 2 pi times 1 over u du equals overall negative 1 over 2 pi, be in brackets log u from infinity to 1.
Good. Okay. Yeah, so now we have a pretty serious problem, because when we combine these two integrals, it naively seems like the expectation value that we're going to get is something like infinity minus infinity, right? Because it seems like the combination of these two, splitting the integral into pieces, is going to give us a 1 over 2 pi, I mean, I'm going to write equal sign in scare quotes here because this is not actually equal, but it seems like the expectation value is supposed to be something like 1 over 2 pi times something which is like infinity minus infinity, but this thing is not actually a well-defined number, right? Infinity minus infinity is something called an indeterminate form, which sometimes you have to use L'Hopital's rule to evaluate or something. So this thing is actually undefined, so I should really not put scare quotes around it. I should say this thing actually is equal to, the quantity which simply asserts that this number does not exist, right? This is not a well-defined, nice integral that has a specific numerical value unambiguously. So this is what I mean when I say that the mean or the expectation value doesn't always exist. It can be that the probability distribution goes to 0 so slowly at infinity that the average value is just not a well-defined number. Right. So I think I have this more in a slightly different way in the previous slide. So why did I think I said something wrong here. Log x squared. Yeah, I didn't do a u sub. So this is a slightly different way of seeing the same thing, because if you don't do the u sub and you just say, look, the integral of x over x squared plus 1 is basically a half log x squared plus 1. Right? If you don't do the u sub and just say this is the antiderivative without changing variables, then you would say this thing is supposed to be roughly log x squared plus 1 evaluated at the endpoints. And if you try to remind yourself of what the definition of one of these improper integrals is, it's really the limit as c goes to infinity of this thing evaluated at the two endpoints, right? But the problem is that this thing is symmetric, so when I plug in c or minus c, this thing becomes positive in either case. So you can actually just by symmetry take this to be twice the limit as c goes to infinity of this thing from 0 to c, and at 0 it vanishes. So the quote-unquote answer you would get is 1 over pi times the limit as c goes to infinity of log c squared plus 1, which is again undefined. So, I mean, regardless of how you compute this thing, you're going to get something which is not a nice, well-defined numerical answer. So, anyway, the upshot is, if you remember nothing else, remember that the Cauchy distribution does not have an average value. Said differently, this thing goes to 0 so slowly at infinity that it's like saying that this thing has a fairly high chance of outputting a large number, no matter how large that number is. So for that reason, the average output is somehow infinite, right? It's an intuitive way of seeing what we just saw analytically. But the point is there's no mean, and there's no higher moments. As we'll define next time, higher moments are the integral not just of x, but of x raised to the power n times the probability distribution f of x from minus infinity to infinity. So these are nth moments. So the nth moment is the same thing with this thing just replaced by x to the n power. And as you can probably see, this thing, raising this to a higher power is only going to make the problem worse, because if we make this, x to 100 upstairs, this thing is only getting big faster at infinity, so it only becomes more infinite, which doesn't help us. Yes, cough indeed. But anyway, more on that next time. But for now, questions on...
I was not coughing to say you're getting sidetracked. I was coughing because I was coughing.
Okay. I thought it was meant to be a commentary on what I was saying. But, okay, good. So is it clear why the integral which would define the expectation value for this guy actually doesn't exist?
Yes.
Good. Other thoughts on Cauchy?
Nope.
Okay. Good. More stuff. Fuck.
Is it another challenge?
Well, they're all heavy... They're all challenges. They're all heavy tails. I can't talk. Yeah, what was I saying? So when I showed you the Cauchy distribution plot, you said, oh, it looks like a bell curve. And it basically is, but I just want to talk about the tails for a moment. So for an exponential, so this is like the bell curve e to the minus x squared. And when we're talking about the tails, we're just discussing how quickly does this thing go to 0 when x is large, right? So we saw a long time ago in the limits chapter that exponentials go to 0 much, much faster than polynomials or 1 over polynomial or whatever. So the point of this entire exercise was to show you that since the Cauchy distribution roughly goes like 1 over x squared when x is large, it's really x squared plus 1, but if x is ginormous, we can just drop the 1. This guy roughly goes like 1 over x squared. And the point is that 1 over x squared definitely goes to 0 when x is large, but it goes to 0 much more slowly than e to the minus x squared. So if you have a probability distribution that goes to 0 at the rate of an exponential, you normally say it is light-tailed. Light-tailed because the tail, the part where x is large, it's very thin, the distance between this and the axis. If this thing does not go to 0 like an exponential, but rather like some power of x, like 1 over x squared, which is x to the power minus 2, you say the distribution is heavy-tailed. So these heavy-tailed distributions actually come up quite frequently. They're sort of the bane of financial managers, because if you are modeling the motion of a price in some financial market and you assume that it's a Gaussian, because that's very simple and Gaussians come up all the time, if you assume it's an exponential but it's really a heavy-tailed distribution, then you're really missing out on all this stuff which is called tail risk. So tail risk is just the observation that if your PDF is heavy-tailed, there's actually a pretty large probability of huge price moves where you would think that there's almost no probability of that because you're assuming a light-tailed distribution. So if you model price moves with a light-tailed distribution when in fact your price moves are heavy-tailed, as they almost always are, you're going to have a lot of these so-called black swan events where the price moves by a fuck ton and you're like, how could that have ever happened? My probability was so small at such a large price move. And then someone comes along and says, yeah, well, your probability distribution was wrong. You thought it was really small at that price move, but it actually wasn't that small because it's heavy-tailed. So if you don't want to lose a lot of money on black swan events, you should use heavy-tailed distributions, even though they have bad mathematical properties, like having an average value which is undefined. Still important.
I have no idea how this is related to your part in finance as, to my knowledge, machine learning.
Well, I mean, no comment, but yeah, I mean, it's
no comment because NDA, or no comment because Wolsey?
Well, the NDA is, I think, expired now. It was 2 years from... Yeah, it's expired. So I could actually just tell you, but it would take rather a while. I mean, the point is basically just like you're modeling price moves with some machine learning algorithm that takes in inputs and spits out an output. But yeah, you should, I mean, your machine learning algorithm will have some assumption about what the distribution of those outputs should look like. So, I mean, the distinction between light-tailed and heavy-tailed outputs is actually quite relevant for your machine learning algorithm.
Okay, so you're predicting what the prices of the stocks are going to be more so than you're predicting, well, training a machine to act on it.
No, there's two.
Or maybe equal parts. I
Yeah,
don't know.
I mean, a trading strategy. So, well, let me take 10 seconds to explain this. So, a trading strategy always has 3 layers. So, there's the signal layer. Signal feeds into the model layer, which feeds into the monetization, which I won't be able to fit in one box. Monetization layer. So what I spent most of my time on was actually in the model layer. The model layer itself is machine learning. So the machine learning is really just like you feed in the signal, which is usually just something like prices or volumes, and you feed this into some machine learning algorithm, and it's going to spit out a prediction for the price move. So the question you were asking is what you did mostly machine learning, or is it mostly acting on predictions? And the answer is both, right? They're two separate, unrelated parts of the process. So you can make more money either by having a better model, which is to say you make a better machine learning algorithm so that when you spit in, current prices, it will spit out a better prediction of what the price is going to be, 10 milliseconds from now or something. That's one way to do it. A second way is to say, okay, I don't care how good the predictions are, maybe they're all right, but what I'm going to do is have a smarter monetization strategy, which is to say, given how good my predictions of the future price move are going to be, I'm going to decide whether to buy or sell based on that. And you could do some very clever stuff using, stochastic control and various mathematical techniques in the monetization layer, even if your model isn't super great. You can be very clever. So the stuff I'm talking about on this slide is actually mostly what I would call the model layer. Because in the model, you're spitting out price moves, and if you assume your price moves are light-tailed versus heavy-tailed, you'll get very different results. I mean, in one case, you'll be rich, and in the other case, you'll be out of business. So, yes. Long diversion, but is that basically what you were asking?
Yes.
Okay. Good. Other questions on this?
No questions.
Inhale. Okay.
Yep.
Okay, let me step back and just give you a long fucking list. So this has been kind of like, I'm trying to cram, as I did with the matrices unit, when I tried to teach you all of linear algebra in 4 meetings, I'm trying to do basically all of a probability course like 1805, which if we follow the thing I wrote on Evernote, you'll actually do in its entirety. But I'm trying to do all of 1805 in like 2 weeks. So let's just recap all of the different distributions, so all of the probability functions we've seen so far. So the first one I introduced to you when I was trying to convince you that for continuous outputs, it doesn't make sense to talk about the probability of one specific number anymore, right? It only makes sense to talk about the density per unit length for probabilities in that interval. And I said, here is one example. Consider the uniform distribution that gives you some number between 0 and 1 with equal probabilities. So that was the first PDF we saw, was roughly spit out a random number between 0 and 1 where all of those numbers are equally likely. So it's very stupid. It's like the dumbest distribution. Fine. I hear crashing. Good. So then the second one that we saw, which is actually the most important, is the Gaussian distribution. So a Gaussian is like e to the minus x squared, maybe with some mean and some variance or something. So the explicit functional form looks like this, given mu and sigma, where sigma measures the spread. Roughly, sigma is like how wide this is. And you have already seen that come up in a very natural way in diffusion and the random walk, right? Because when you did this diffusion equation, you found that the solution, the answer for the density of random walkers when you start them at the origin, is exactly of this form where sigma squared, this thing that appears both in the exponential and in the prefactor, sigma squared in your problem was 2 times the diffusion constant times time. So I just want to rant for one moment, because you're going to see this object over and over and over as you study science for the rest of your life. It comes up many, many times. This object is called the heat kernel. So when you see an object which is a Gaussian whose spread, the width of the Gaussian, is linearly increasing in time, right? The width is just some number times time. which is to say this is an infinitely skinny Gaussian, which is it's just all of the random walkers are at the origin when time equals 0. And then at later times it becomes, first it's a kind of reasonably skinny Gaussian, then it becomes a very wide Gaussian, and then at long times it becomes basically flat because the spread keeps getting longer and longer. That thing is called the heat kernel. So let me just look at a visualization of that. Here is Wikipedia telling us about what the heat kernel looks like. So let's just see the animation basically. So this is basically the probability distribution for your random walkers, and it's going to start over in just a minute. Let's wait until it's very highly peaked at the origin, because that will be the beginning when we start all these guys. So it's taking, there we go. Okay, so now it's hugely peaked at 0, and then as you see, it spreads out very, very quickly. So what we're seeing is a Gaussian at every time, but at time 0, it's a super sharply peaked Gaussian at the origin. So the density of random walkers at the origin is huge at the beginning, because we start all of them there. But then at later times, they immediately start to spread out very quickly, because we assume these guys move to the left or right with equal probabilities. So over time, the density of the random walkers is going to spread out so they get flatter and flatter, but still occupy a larger and larger range of this, the real line. So this thing is the heat kernel, and you'll see it, at least in 3 different equations. You can ask, why is this called the heat kernel? We're studying this in the context of diffusion. Well, the diffusion equation is basically the same as the heat equation. The heat equation is, the derivative of f with respect to time is 2 derivatives of f with respect to x. And I'm using curly d's. Whenever you have a function of 2 variables, like f of x and time, when you have 2 variables, it's customary to use this curly d, which is called a partial derivative, and you'll meet very soon in 1802. So you use a curly d instead of the usual d when this thing depends on 2 variables. But anyway, so whenever you have this case where one time derivative is roughly equal to 2 space derivatives, possibly with a constant d in front, but that doesn't matter. Whenever that is true, you say this is an equation of heat type, so this is a heat equation, or as you saw before, this is a diffusion equation. This is also what happens for the free Schrödinger equation in quantum mechanics. So this is simply the statement that if you take the wave function for some particle like an electron, and you start the electron, the electron is very close to the origin at time 0, and then you wait some time, the probability distribution for the electron is also going to spread out so that it becomes this wide Gaussian at later times in quantum mechanics, which you'll study in a physical chemistry course or quantum mechanics course or whenever you see this. So anyway, maybe it doesn't make a lot of sense now, but I'm just flagging this, that you will see this many, many times when you study how heat spreads out in a hot metal rod, or diffusion in 3091, or Schrödinger in physical chemistry. This heat kernel is going to come up over and over and over. Good. Okay, so before more ranting, questions or thoughts on the first 2?
I do not have any thoughts, comments, questions, or concerns. I'm amused by you saying when. I see this, not if.
Well, I have high hopes. If you never learn about the heat kernel, then something will have gone terribly wrong, like you got hit by a bus or something. Okay, good. So what else? So there's also this Maxwell distribution, so I'll try to go more quickly through the rest, but the Maxwell distribution was the PDF for speeds in an ideal gas, which we saw last time, and I'll say a little bit more about next time. But roughly this guy was almost a Gaussian. It's like e to the minus v squared, but it's all multiplying a v squared. Right? So instead of looking like a Gaussian, this was like a lopsided Gaussian, where it could only be positive values, basically, because v is supposed to be the length of the speed vector. So that made sense. We also spoke about hydrogen in the ground state. You can ask, if I measure how far from the nucleus is the hydrogen, it's the electron in the ground state of hydrogen. This is the PDF for that radial distance. as we met.
This is graphing 1s1, right?
Yeah. This is the 1s1 orbital, and then all of the higher orbitals have different radial dependence, but they also have different angular dependence as well. I'm only showing the dependence of the distance from the origin, not whether it's likely to be, at theta equals 0 versus theta equals 90. So especially, already starting with the p orbitals. So 1p1 has, some theta and phi dependence. And the theta and phi dependence is encoded in these functions, which are called spherical harmonics, and they are written as YLM of theta phi. So these are spherical harmonics. So yeah, that's why I'm not talking about those, because it's somewhat more complicated to discuss the spherical harmonic dependence on angle. But for 1s1 at least, it's actually quite simple. It's just no dependence on theta or phi, just dependence on r, like this. Yeah, that's why the ground state 1s1 is very nice. Good.
I'm looking at 6.
6.
And I'm just trying to comprehend why circles come up in everything.
Yeah, so, okay. Well, 5 is obvious because we discussed it today. When I was writing these slides, I thought you would already have done the daily challenge for, I guess not tomorrow, but the next day, because
Whoops.
I misjudged the amount of time these things would take. But anyway, what you're going to do, I guess on Thursday, is in Python, rather than generating random numbers, what you're going to do is generate some random matrices. So you're going to do some, random 2x2 matrix like this, for instance, and NumPy will spit out some matrix filled with random numbers, and then you're going to find the eigenvalues of that random matrix. So you'll write some function like random matrix experiment where you generate a bunch of random matrices, you find the eigenvalues of all of them, and then you put them in a list. And then you just plot, how often does each eigenvalue appear in that list. And the answer that you're going to find is something called the semicircle distribution. So the semicircle distribution is basically just, if you just have on the x-axis, so here are all of the different eigenvalues lambda, and then here is the frequency, or the probability, if you will, the frequency of the eigenvalue lambda. On the y-axis, you will find something which looks roughly like a semicircle with some radius r, which you will find in Python. So the most famous place where this semicircle distribution comes up is indeed in the eigenvalues of random matrices. So this is a very nice connection between the matrix stuff that you did, several months ago and probability, because now you'll just say, okay, I'll find the eigenvalues of a bunch of random matrices and I'll put them, in some chart, some histogram, and see how frequently they come up, and you get this very nice, clean, quite elegant answer about this, semicircle law, which historically people found quite interesting. So anyway, so that will be Thursday and Friday. And then we also saw this Cauchy, this weird distribution that has no mean or higher moments, a couple slides ago. Okay, I have one more topic which I've broken up into 6 slides of challenges that hopefully should be reasonably easy. But before doing the final topic, questions on this quick list of all the PDFs that we have seen?
I do not have any questions.
Good, okay. Alright, fuck, why did I zoom? Damn it. Not what I wanted.
You done gooped?
Done fucked up.
Do you mind if I grab a soda quick?
Yeah, sure, I'll be here.
It's 2 through 8, and I have no idea. This is a question I've been wanting answered for a long time.
Good. Well, I think you said 2 through 8, so I started filling in the table. But, alright, so we're going to have to do some counting, but let's...
There is one way to get a 2. Yeah. There are 2 ways to get a 3.
Well, hold on. So I
There
guess
are,
okay,
I don't know.
I guess we need a different column because what you just told me is the ways to get it, right? So that's different from the probability. The probability is the ways to get it divided by the total number of outcomes. So indeed, there's only one way to get a 2. Tell me again, how many ways are there to get a 3?
2?
Yeah, so you get a 2 and a 1 or a 1 and a 2. Good. How many ways to get a 4?
There's 1, 3, 3, 1, and 2, 2.
Yeah, so there's
And there's 2 ways to get 2, 2, so I guess 4.
yeah, so yeah, 1, 3, 3, 1, 2, 2, or the other 2, 2, right? So 4 ways. Good. How about a 5?
You know what? I'm going to go through it all anyway, even though I think I see a Fibonacci. Let's see. 5, 1, 1, 5. Well,
4, 1.
let's just. Oh, right. Let's just double the number that we count for one way. So 1, 4, 3, 2. Wait, no, that's not also 4. Yeah, that's not quite right.
Yeah, so you say there's 1, 4, 2, 3, 3, 2, or 4, 1. So it seems like it's just...
Yeah, so it's 4.
Okay. And now by symmetry, it has to be the same the other way around, right? Because there has to be the same number of ways of getting 4 as 6, because every combination of 4, every combination that gives 4, we can map into a combination that gives 6 by just subtracting 4 minus the results from each of the 4 ones, right? So like 1 plus 3 gives you 4, but you just switch the 1 in the first results to a 3, and the 3 in the first results to a 2, right? And then...
Rapid blinking.
Okay, well, you see what I'm saying, I guess, that this thing should be symmetric, so, I mean, we can fill the rest of them in. For instance, there's only one way to get 8, which is 4 and a 4, right? So let's make sure we've counted all of these correctly, because we know the total number of ways should be 16, right? Because there's 4 choices for the first die and 4 for the second. So does this add up to 16? Well, 1 plus 2 is 3, 4 plus 4 is 8, so we have 11, plus 4 is 15, 16, 17, 18? Did I
Wait,
add
what?
that? Something seems wrong. One of these must
12 plus 4. Oh, wait.
4, so this is 12. 12 plus 3 is 5, so it looks like we have 18. So one of these is wrong. Which of them is wrong?
Inhale. Let's see. How many ways are there to get... You can't get... Oh, wait, you can get 6. So 6 Henry Belt. 2, 4. 3, 3. 4, 2.
Yeah. Oops. That's 1. Yeah, so you say 6.
So 6 is right.
Yeah. And I think 4 is also right, because this could be... 4 could be 1, 3, 2, 2, the other 2, 2, or 3, 1. So I think this is right. Was the 5 correct?
Are we supposed to be double counting?
Let's see. So is 2 on the first? I think so, because the total number, if we say the total number is 16, 4 times 4, that means there's 4 choices for the first and 4 choices for the oh, maybe not. Okay. So you say if there's 4 for the choices for the first and 4 for the second, is 2 and 2 really different from 2 and 2? No, I guess not. Okay. So I fooled myself. So this should really just have been, the 4 should have just been 1 and 3, 2 and 2, or 3 and 1. So there should have only been 3 here.
Okay, so 2 rolls of 2. I mean, 2 double rolls of 2 are not unique.
Yeah, 2, 2 is the same as 2, 2, in other words. Good.
Whoa.
Alright, so is this now correct? 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 3 is 13, 14, 15, 16. Good, so this must be correct. So the probabilities are just dividing all of these by 16, 1 over 16, 1 over 8.
1/8, 3/16, a quarter, 3/16, 1/8, 1/16.
Good. I don't know if I even wrote solutions for this. Nope, I didn't write solutions. But I'm...
General sum of RVs.
Yes, random variables, not recreational vehicles. But good, okay, so this is correct. You could say, okay, why did you make me do this? This has nothing to do with calculus. The answer is yes, but this will suggest what we're going to do for the, more general case. So what did we do to get our answer in this case, right? So if you wanted to know the answer for a particular outcome of the sum, right, like 4, what did you do? You added up all of the possible ways that you could get outputs from the two separate summands, the two independent random variables you are adding together to get your output, in such a way that their sum was the output you're interested in, right? So in order to find the probability of getting a 4, we had to add together all of the ways of getting a 4, which were again 1 and a 3, a 2 and a 2, or a 3 and a 1. So in other words, we are adding up basically all of the probabilities, so probability of 1 times the probability of 3, or a probability of 2 times the probability of 2, and a probability of 3 times the probability of 1, right? Each of these are a quarter times a quarter, right? Because these are independent events. So what we really did was add up the product, the sum of all products of probabilities for two outcomes, which added up to 4, right? So since 1 and 3 added up to 4, we said a quarter times a quarter is 1/16. A quarter times a quarter for the two 2's is 1/16, and a quarter times a quarter for 3 and 1 again is 1/16, and 3/16 is the answer. So that is how you find the probability distribution for the sum of two random variables in the discrete case. So now I'll give you a harder problem, which is the following. Now these are continuous, so it's not just dice rolls, these are functions with integrals. You have one random variable x, whose PDF is f of x, and a second random variable y, whose PDF is g of y. And I ask you, can you write down an integral expression for the probability distribution of their sum? Or in other words, if I randomly pull one x using this distribution f, and then I also randomly pull one y with this PDF g, and I add x and y together, what does the probability distribution look like for that sum, h of z, say, for the sum z is x plus y? Think about that for a moment, and let me know what you think.
Okay, so the sum of these two functions would give us, for example, a graph of potential outputs.
The sum of the functions f and g, say?
Yeah.
Well, that's not going to work. I mean,
that's not how random things work.
No. So let's take a simple example. So if f and g are both random numbers between 0 and 1, right? So f and g are both random numbers between 0 and 1. Then f is this function, which is 1 between 0 and 1, and so is g. But if we add together f and g, now we get some function which is 2 between 0 and 1. So that's not even a probability distribution anymore, because now its total integral is 2 instead of 1, right? So I think you're thinking along the right lines in that there is a...
I mean, I had a different idea going on. I was just curious how that went.
Okay, well, what's the different idea?
So this is asking for the probability distribution of their sum. Is this asking for, well, probability distribution? Inhale. The random variable is x.
Yeah, good. Let's go back to the discrete case just for a quick intuition check. So
I mean, we can solve that equation for just y, and solve that equation for x and substitute it into f of x.
Okay, so you say consider all the probabilities of getting f of, say, z minus y or something. Okay.
Yeah.
Okay, that's a start. Okay, good. So now this thing gives me the probability of getting some output which sums to z, some number z, if I add it to y. Okay, so now what should I do with those two numbers, this f of z minus y and this g of y, in order to get the total probability of all ways of getting an output of z?
I guess we write the integral from, I don't know what values.
Well, the
So
probabilities,
I
so it should
guess.
probably be the whole line, but yeah.
Oh. So it's going to be from negative infinity to infinity of f of z minus y plus g of y.
Y plus, why are you adding probabilities? In the other example, we multiplied them, right? If you wanted to find the probability of getting the sum equals 4, right? It was the probability of, say, 1 times the probability of 3, right? Because the probability you get 1 on the first die roll is a quarter, and the probability you get 3 on the second die roll is a quarter, and then we add
Alright.
to p. Yeah.
I remember.
Good. So it looks like we multiply probabilities, right?
So f of z minus y times g of y.
Good.
dy.
That looks right. Yeah. So let's just think about this, because this is an ugly fucking formula. And the first time students see this, they flip shit and tell me, what does this mean? This is the stupidest thing I've seen in my life. What are we doing? This is
Z constant?
Yeah. Well, z appears on the left side. We're trying to define a function of z. So you plug in a particular value of z, and then you do this integral. So what is this doing? Let's think back to the discrete case. So if I do one die roll, so 1 dx, and then I have a second die roll 1 dy, and then I ask, what is the probability distribution for the sum equal to z? Right? What would I do? Well, the probability that the sum is equal to z should be, you add up all possible ways of getting, if this thing has some probability f of x, I say, and this one has some probability g of yj, and you say, all right, I roll the first die, and it gives me some outputs x with probabilities f of x, and I roll the second die y, which gives me some outputs yj with probabilities g. How could I figure out the probability distribution for the sum equal to z? Well, it's actually quite simple. You just add up all of the possible outputs, I and j, for the first two dice, such that the sum of the two outputs is equal to z. So what I would do is I would add up the sum of all f, which are z, the output I want the sum to be, minus yj. I guess it's not really a sum over I anymore, it's just a sum over j, times g of yj. So what is this doing? It's just saying, if I want to find the probability that my sum of the two, say, d4s is equal to 4, I add up all ways of getting two outputs from the two dice equal to 4 in sum, and the first die plus the second die have to add up to 4. So if z were 4, then the first die would have to give me 4 minus some number, the second die would have to give me that number, which add to 4, and I add up all of the possible contributions of that second number. So all that we've done is go to the continuous case where we replace this sum by an integral. So in this case, all we're doing is saying you have some first probability distribution f, and you have some second probability distribution, say g, and you want to find, okay, what is the probability that I add these two guys together and I get, say, 0, right? If you want to find the probability that you add up these two guys, f and g, and get 0, you have to add a lot of different contributions, because maybe f outputs this number here, minus x, and then g outputs this number here, which is plus x, and they add together, which give you 0. So I better take the probability f at minus x times the probability g at plus x and multiply them together. But there's another possibility. Of course, maybe I get, f outputs some different number, which is way over here, which is, say, minus y, and g outputs some number which is way over here, which is plus y. I had better account for that contribution as well, which means I take the probability that f gives me minus y times the probability that g gives me plus y, and I add those together, or I multiply those together, and I should add up all of those possibilities over the infinitely many choices of one number along f and one number along g to give me the sum z. So that's what this integral is doing. It's adding up all possible ways that you get one number from the f distribution and a second number from the g distribution, such that the sum of the first and second numbers is this z that you're looking for. Sounds very complicated, but
it's clear.
Okay, that makes sense. Good. Thoughts on this?
No, but did we answer the question?
Yeah, this is the correct answer. So
Oh.
let me show you. So we were asked to write an integral expression, and what you told me was exactly right, although I think you plugged in for x instead of y, and I plugged in for y instead of x, but they're both correct. So yes, indeed, what you do is you add all probabilities which are a product of f of x and g of y such that the sum equals z. So I'm going to show you a picture to explain what we're doing here, because you might remember from a long time ago that if you have some function f of x which has some shape like this, and then you ask, what does the function look like if I offset this by 10 or something? If I add 10 inside the argument, well, that means that, for instance, the value that this guy output at 0, well, I'm adding 10 inside the argument. So the value that this guy output at 0 is now going to be output at minus 10, because minus 10 plus 10 equals 0. So I'd better move this guy to the left by 10 units, so that this output, which before was at 0, is now going to be output at minus 10. So the punchline is that if you add some number inside a function, it's going to move it to the left or the right by some number of units, where here this distance is supposed to be 10 units compared to the origin. So anyway, there's a very nice visual interpretation of this product, f of x times g of z minus x, because this g of z minus x you can interpret as basically g of minus x shifted by z, right? Because of this picture I just drew on the right. Because if you shift by some number inside the function, it moves it to the left or the right. Okay, so for one fixed value of z, the junk in here is some function f times some function g shifted by z. But then you say, all right, you're not just shifting by one z, you're supposed to be integrating, right? Well, you're shifting by one z, but you're integrating over all x's, right? So it's kind of like you're shifting by a fixed offset, but then you are moving this guy from minus infinity to infinity, where the total shift inside the g is somehow moving from the left to the right. So there's a way to visualize this integral which involves holding the first function at some point in space, and then you take the second function and slide it past the first function. By slide, I mean you literally just change how much you are shifting it by, to the left or to the right, and then when these guys intersect, which means their product is non-zero, you just add them up. Okay, so that probably makes about 0 sense. So let me just go to the picture. I want to use this animation. Okay, so let's look very carefully at what's happening here. I actually just want to refresh because we're going to slide. I want to start over. Good. So we're sliding this red curve past the blue curve. And then once they intersect, we are integrating the product of the two of them. So by product, I just mean when this guy slides past the blue curve in such a way that the product of red times blue is non-zero, we're just going to count that and start accruing it, right? So whenever the product of these two is non-zero, it's highlighted in yellow and it's added to some counter. And then the final curve shown in black at the bottom is the total value of that counter, right? So now as you see, once these guys slide past and they totally eclipse each other and overlap, the counter is increasing very fast. So this triangle is, it's very large in its output. But then once the red curve is sliding past the blue curve, the size of the yellow overlap is very small, so this thing is not increasing very much, and eventually it goes to 0 when they don't overlap anymore.
And the integral of that black line is equal to the two totally overlapped, it seems.
Yeah, it does look that way, right? Because this guy
It's
has...
probably just because they're the same size square.
Yeah, because they both have area 1, and the triangle has area a half times base times height, so a half times 2 times 1, which is 1. Yeah. That might be a coincidence.
Coincidence.
Yeah.
Random thoughts.
Let's look at another one, which is slightly less trivial. I don't think it'll be true here. So we're going to slide the red past the blue, and again, once they overlap, we start incrementing a counter. But now the shape is very different because they continue.
Huh.
You see what's going on?
Is okay.
It's pretty interesting.
That's weird.
Yeah, it does this weird, like, I mean, there's a kink. You see at 0.5, there's a kink where the slope changes kind of discontinuously, right? So this guy has a first derivative which is discontinuous. It's very weird. But anyway, let me go back.
It looks like it follows the blue curve.
Yeah, towards the end it follows the blue curve exactly, which, I mean, asymptotically that will be true just because this guy is, some bump function. But good. Okay, so let me just go back and explain why that's what we said, basically. So again, all we're doing is sliding the function g past the function f. By sliding, I mean translating by z. And when they overlap, we multiply the two of them and add up the overlaps. So that was the yellow area is the overlap. So this is a stupidly important operation, which is called the convolution. So you have now learned many ways of combining two functions to get another function, right? You could take two functions and add them, like f plus g, like, I don't know, x squared plus x cubed. You add them together and get a new function that's kind of stupid. You can compose them, f composed with g, if, I don't know, f is x squared and g is sine of x or something. You could compose them and say now this is sine of x quantity squared. That's another way to combine two functions and get a new function. Now you know of a new way to combine two functions and get a third one, which is called the convolution. This thing is the convolution. So the convolution of, say, x squared convolved with the sine is, by definition, the integral from minus infinity to infinity of x squared times sine of z minus x dx. And I should emphasize that the left side is now a function of a new variable, z, right? So the left side depends on z, the right side clearly depends on z, because z is a free variable and we integrate out x, so the right side doesn't depend on x. So you should think of this funky convolution thing as a machine which takes in two functions f and g and returns a new function, f convolved with g. And by the way, for fuck's sake, don't sound like a newbie person and refer to the verb form of convoluting, quote-unquote, two functions as convoluting, right? Don't say, I convolute f with g. That's not what you say. The noun form is convolution. The verb form for convolving two functions is convolving. So if you would like to take the convolution of f with g, you say, I am convolving f with g. You will sound very stupid if you say, I am convoluting f with g, in the same way that beginning calculus students sometimes incorrectly say, I am deriving f, when they mean I am differentiating f. The verb for taking the derivative is not fucking deriving the function. You differentiate the function to take its derivative. In the same way, you don't convolute two functions. You convolve two functions to take their convolution. For fuck's sake. Don't say
I just hear myself saying, I derive.
Well, don't do it anymore. It's one of those things like pronouncing latex as latex. You just don't do it.
Because once you know, you can't not know.
I hope so. But anyway, now I'm just getting angry at no one in particular. So anyway, fine. So again, let's just look at the picture. What is convolving two functions doing? It's very important not to forget the picture. All we do when we convolve two functions is start with some blue curve, f, say, and start with the second curve, g. And you think of this as sliding one past the other. So we slide g past f, and whenever they overlap, we just take this product of all of the places where they overlap, which means we are multiplying f times g wherever they overlap, and then we define a new function defined by, this aggregated overlap between the two of them. So you're going to see this again. I mean, the most natural way to think about the convolution is what I just told you from random variables, that if you have two, weighted dice rolls and you want to know what is the probability for their sum, you convolve the two probability distributions. So I think the way that everyone should first learn convolution is the way to get the sum of two random variables. I mean, that's fine. We're going to learn this again when we do the Fourier transform, because the Fourier transform for signal analysis also gives you a very natural way to think about the convolution in terms of how one signal in some electronic system affects the shape of another signal. But I mean, if you talk to any electrical engineers who never learned probability and they were just shown the convolution out of fucking nowhere in their signal analysis class, they act like it's the work of Satan. Like, you say convolution and they cower in terror. Like, the convolution, it's so complicated. You have the integral of a product of two functions and they have different arguments. What does that even mean? It's not fucking magic. You just take one function, you slide it past the other, and you add up their products where they overlap. Like, it's, I don't know. I don't know why I'm so angry, but it's actually quite simple.
Inhale.
Okay. Last thing, unless there are questions on convolution.
Yep, challenge, knew it.
Yes. Okay. So
Let's
I'll
see.
ask you to use the convolution now to get that triangle that we saw in the first animation. So now I say we draw two random real numbers that are equally likely to be any number between 0 and 1. So it's basically some function. This probability is f of x, which is basically 1 or 0, where it's 1 if the number x is between 0 and 1, and 0 otherwise. So anyway, so I draw two random numbers that are between 0 and 1, with all numbers equally likely, and I add them together. So I'll ask you, what is the probability distribution for their sum? Or in other words, what is the convolution? What do I get when I convolve f with f?
I'm thinking.
Good.
So should I write this as an integral?
Yeah, we can start with that. So if we use the notation before, the definition of convolution was, I'm just copying it from the previous slide. So this should be what? F of x times f, because it's the same function. We're convolving f with itself, because both of these variables are drawn from the same distribution, but the argument changes. So it's x over here, but it's z minus x over here, because they have to add up to z. So this dx. So the hint is that, okay, this integral from minus infinity to infinity is very complicated, but I'll ask you to split it into two pieces, because this function is very simple, because the function is only non-zero between 0 and 1. So I'll ask you to split this thing into two regions, split this integral into two separate pieces, because either this first guy, x, is between 0 and 1, so the first guy is non-zero, or the second guy, z minus x, is between 0 and 1, and hence the second factor is non-zero, or both. So how can you split this up using that information?
So we can break this into the integrals 0 to 1 and 1 to 2, since negative infinity to 0, I believe, let's see, negative infinity to 0 at 0.
Well, z can be anything, right? We don't know what range of z is allowed yet. So the first thing you just said is okay. 0 to 1 is good, because when x is between 0 and 1, we know that this first guy is non-zero, for sure, right? Because this plot is, 1 between 0 and 1. So, oops, fuck. So in the first integral, if x is between 0 and 1, this thing is certainly good. That's fine. What should the second integral be if we want z minus x to lie between 0 and 1. It'll be a little different.
We are going to be integrating from 1 to 2 of f of x times f of z minus x.
Yeah, good. How could you have figured that out besides just looking at the hint? What's the reason?
Let's see what visualization we can do. It seems like at 1 the slope is going to swap. But, well, that doesn't mean anything.
Yeah, so this isn't actually correct. So
yeah, it should be 0 to z, z to something.
well, let's be careful. So we want the second guy is z minus x, which we want to lie between 0 and 1. So we want 0 is less than or equal to z minus x is less than or equal to 1, right? Because the second guy has to be between 0 and 1. The first guy, x, also has to be between 0 and 1 because the product must be non-zero. So x is between 0 and 1, and z minus x must be between 0 and 1. So my question to you is, if I have some number between 0 and 1, and then I have a second number which I don't know shit about, z, but I subtract a number between 0 and 1 from z, then what must z lie between if this difference is supposed to be between 0 and 1?
Let's add the... No, adding inequalities doesn't... I don't think it doesn't work. I don't think it works like that.
Well, we could add them, but it's going to double count. So, all right, so what happens if we add them? If we simply add these, 0 is less than or equal to z is less than or equal to 2, so that's true. I mean, that was kind of obvious, right? Because if we add together the two outputs of a random number between 0 and 1, we're certainly going to get a random number between 0 and 2, because at worst, I get 1 from the first and 1 from the second, right? So that's fine. But we're splitting this into two pieces, so we have to be a little more careful, right? The first piece is that x lies between 0 and 1, right? So the second piece should account for the pieces where x itself, let's see, what do I want? I want x, now I'm confusing myself. I should look at what the split is. Yeah. So, yeah, the problem is, the problem is I've already said something false, because in the first case, we want the product of both of these to be non-zero. So x is between 0 and 1, which means the second piece, the z minus x, must also be between 0 and 1, which means, in fact, x must be between 0 and z in this case. There we go. Is it clear why it has to be up to z? Because the second piece is z minus x. Good. Okay. So that was where I confused myself. Good. So the first one is 0 to z, which means the second one, I think, should be indeed from z minus 1 up to 1. Why z minus 1 up to 1 on x? Well, because, oops, fuck, having a bad time. There we go. Z. So the second one should be z minus 1 on the x up to 1, because at the lower bound, when x is z minus 1, then this f is going to be z minus the quantity z minus 1, which is 1, right? But at most, when an x equals 1, this guy is going to be z minus 1 on the second piece, and we know z lies between 1 and 2, right? So this thing will, if you take a number between 0 and 2 and subtract 1, you're going to get something between 0 and 1. Okay, so in both of these cases, we've split it so that both the first and second factors are non-zero. So now I'll just ask you, knowing now that in both of these integrals, the arguments of f lie in this range, 0 to 1, where this function is equal to 1, I claim you can just evaluate the integrals. You can just write down the answer. So what should I do to evaluate the two of these now?
Sorry, I am thinking.
Okay. Is this really plus, or is it two cases? Or is this piecewise? Now I've confused myself. Does it depend on where z... Oh, yeah, this depends on where z is. Yeah, I said something stupid. Fuck. Sorry. This depends on the value of z. It depends on whether z is between 0 and 1, or z is between 1 and 2. Yeah, this should be piecewise. Yeah, I totally botched this one. So should be piecewise 1 less than z less than 2. Okay, so why should it be piecewise? If z is between 0 and 1, then the only way that the product of both of these can be non-zero is if x is between 0 and 1, and also z minus x is between 0 and 1. Right, because x can only run up to z. Yeah, because x can only run up to z, because if x got bigger than z, this second guy would go negative, so that would give us 0 probability. But if z is between 1 and 2, then x can only run from z minus 1 up to 1. This should be less than or equal to. Because then x is between 0 and 1, and z minus x, since z is between 1 and 2, this thing will also be between 0 and 1, because x can be at least z minus 1, and z minus 1 is 1. Alright, I'm fucking this up, but anyway.
I have no idea what's going on.
Yeah, alright, well, we're doing a split. I should review this next time. But alright, anyway, so let's just evaluate both of them, knowing that I should have cooked up this example so that if we've done this right, the function f should be 1 on both of these intervals. So anyway, in either case, all you have to do is integrate 1 between the given endpoints. So what should we get?
Sorry, could you restate the question?
So just evaluate these two integrals when the function f is 1. Literally, that's it.
When f is 1, well. Oh, are you saying when f of x equals 1?
Yeah, so integral 0 to z
Then
of dx, and integral from z minus 1 to z of dx, because it's 1.
Equals z minus 0.
Yeah, so the top one is z, and what's the bottom one?
And the bottom is minus 1.
Yes, it should be.
Plus 1 equals 1.
Yeah, it should be.
Well, trying to say z minus 1.
Yeah. Z.
Well, whereas z minus 1 is in parentheses. Thus equals 1.
That is right, which means I probably made a mistake. Because this was supposed to be 2z minus 1, which means I did this wrong. 2 minus z. It was supposed to be 2 minus z. 1 minus... Oh wait, no. From z minus 1 up to 1 should be... Oh wait, I miscopied. What am I doing? It was 1 over here. It was 1 over here and not z. There we go. So, there we go. It should be 1 minus the quantity z minus 1. There we go. So this is 2 minus z.
Equals, yeah.
This was a transcription error. Okay, good. Good. So I should probably rewrite this more clearly next time, but for now, what have we found? We found that if we split this function into two different regimes, one between 1 less than or equal to z less than or equal to 1, and the second 1 less than z less than 2, we get this piecewise defined function. So let me just plot the piecewise defined function, which should look like this. So when z, why can't I write? 0 is less than z is less than or equal to 1. So when z is between 0 and 1, the probability is just z, so it's a straight line with slope 1. And when z is between 1 and 2, it's 2 minus z, so that's a line with slope minus 1 and intercept 2, which is just going downwards towards 2. So if I had done this correctly, the function we would have found, piecewise defined for z, would have just been a triangle. This is f of z, I guess. A triangle which goes up to a peak of height 1 at z equals 1, and then goes back down to 0 when z equals 2. So that's what I was supposed to have done, and if I had done it correctly, it would have matched the triangle that we showed in this animation. So if we convolve the flat function 1 against 1, you get a triangle. Here it's shifted, so it starts at minus 1 instead of 0, but the point is the same. The triangle rises to a peak of 1, and then goes back down to a probability of 0. So anyway, so I'll redo this next time, but the takeaway message is that if you convolve two uniform distributions, you get a triangle. Or in other words, if you add together two random variables, each of which give you a random number between, say, 0 and 1 with equal probabilities, you'll get a random number between 0 and 2, but now the probabilities are not equal anymore. You are much more likely to get a number close to 1 than you are to get a number close to 0 or 2. And that's just because there are more ways to add together two numbers between 0 and 1 and get a number close to 1 than there are to get a number close to 2. Right? The only way to get a number close to 2 is that both of the outputs of your first two random numbers had to be huge, close to 1, right? Which is very unlikely.
So, a related thought before I forget. Is this, except for integers like the dice, is this some kind of floor or ceiling?
A floor
of a triangle?
Let's see. So you're saying if you... wait, can you explain that again? So where's the floor appearing here?
I'm suggesting, like, maybe between, in this case, between -1 and 0.5, you would have triangle with, well, not triangle, you would have a rectangle between approximately -0.75 and, well, at -0.75, 0.2, or whatever.
So you're always going to get a triangle, but you're saying the left and right sides of the triangle depend on the min of the two functions. Is that right? So if I take a random function, the letter is uniform, U for uniform. So if I take a uniform number between, say, A and B, and then I add to it another uniform distribution between C and D, I'm always going to get a triangle between what is the lowest the lowest output I could possibly get is between, you know, these two is...
I'm suggesting adding the rolls of two dice.
Okay, I mean, this is the continuous version of two dice, right?
Okay.
Yeah, so I mean,
Yeah.
if this is a d4 plus a d6, I'm going to get a triangle between 2 and 10, right? Or more generally, if I have a dice, you know, a dice roll or two die with infinitely many sides, but the lowest number is A and the highest number is B, and I add together a die roll with, again, infinitely many sides, but the lowest side is C and the lowest side is D, I'm going to get some number between A plus C and B plus D, which is obvious, because the lowest number I could get is the lowest from this plus the lowest from this, which in this case is 1 plus 1, which is 2, right? Always the lowest I could get is the min of the two. The highest I could get is the highest from this guy plus the highest from this guy, which in the d4 plus d6 case is going to be 4 plus 6 equals 10. But the point is that all of the numbers between low plus low and high plus high are not equally likely. You are more likely to get something in the middle of the triangle. That's what a triangle means. It's bigger in the middle. You're more likely to get something in the middle than the lower the high. Right? That's the point.
Yes.
Yeah. I think that's what you were saying by the floor and the ceiling, because those are the endpoints, but it's more likely in the middle, right?
I was thinking about less a triangle and more a pyramid.
Okay. So okay, that makes sense. Yeah.
Just thinking about just relations to taking limits and how, like, n equals 3, where n is the side number, you can have a staircase. I don't know.
Yeah, I think that will be...
I don't know.
It's related to the proof of the central limit theorem. The central limit theorem is saying I'm adding together not just 2, but I'm adding together n random variables with all uniform or in general identical and independently distributed. So if I add together, you know, from I equals 1 to n uniform distributions from A to B, right? I think that's closer to what you're thinking of, because it's not just a triangle, it's going to be some shape with a lot of sides, basically, right?
Yeah.
As it turns out, this thing turns into a Gaussian. So it's not actually a pyramid or something, it's always a Gaussian, because the Gaussian is always the answer when you add together a lot of things, if n is large. But anyway, discuss that more next time because we've been going now for 2 hours.
Oh boy.
Good. All right. Yes. Okay. Sorry for the botching that last example, but
No problem.
any parting thoughts or comments?
I brought up all thoughts, comments, questions, or concerns while we were talking.
Good. Good. I appreciate that. Cool. Okay. I guess I should just